Okay, this is the last part of lecture number 7. We're going to talk about strong equivalence principle. And we say if a lab's in falling in the gravitational field, for an outside observer, you see an accelerating lab, accelerating frame. But for the observer inside this falling uh, frame, actually sees no gravity. Actually, it's an inertia frame. And the physics, the different observation from the different observation use different reference frame, we can use physics. Okay. So the question: how to extract further implications from the strong equivalence principle? Just like in special relativity, we can deduce the physical consequences by comparing the observation with respect to different reference frames. But now, of course, instead of frames in relative motion as in special relativity, we're talking about reference frames. One is an inertia frame with no gravity compared with an accelerating frame falling in a gravitational field. So in a free fall frame, there's no gravity and special relativity apply. And on the other hand, the same lab seen outside, which is falling, accelerating in the gravitational field, will uh, see how the observation difference will make from there we can deduce what's the physical consequences. Uh, of course, they say the physics should be the same, even though observed for different reference frames. First, we take a quick look at the bending of the light ray by gravity. Now, we only give a qualitative first look. We're not going to deduce any numbers, and let's just get a feeling because it's very simple to understand. It's just only this stage, only a quality look within the perpendicular to the gravitation field. So if the gravitation is vertical, we're talking about light propagating in the horizontal direction. Uh, Consider a spaceship or shuttle that is in free fall. So observe inside will see no gravity, and so special relativity applies. And if you send a beam of light from height h on the left hand side, it will arrive at height h on the right hand side. So basically, the light is not bent inside this uh, inside this spaceship with respect to observe seen by this observer. However, for an observer outside who sees the spaceship falling, okay, in the gravitational field, and of course, the light would be seen to be bent because uh, this point is below the initial point by a height y. That's the distance the spaceship had fallen. So in effect, we see a bending of light by gravity because in this to this reference frame, there's a gravitational field, and the light is bent. Okay, but normally, so I don't see any place that if I shine a light, we see the light bent by gravity. Well, the reason on in, on Earth the gravitational field is so weak. This is a very tiny effect. It's totally unobservable. Okay, for example, if you even have a lab with a width of 300 meters, say 3 times the size of a football field, and at times the time takes the light to go across only 1 microsecond. So therefore, the distance it falls is 1/2 acceleration time t squared. G is around 10 meter per square seconds. So divided by half is 5, and microsecond 10 to the minus 6, 10 to the minus 12. So this is about 5% of an angstrom. So it's much even smaller than the atomic scale. So so you certainly cannot see such an effect. So it's feasible to only feasible in maybe in astronomical setting where we're talking a long distance and we're talking about stronger gravity. Okay. So anyway, this is just to give you a quality feeling how you can say gravity can bend a light. from equivalence principle point of view. Now we talk about gravitational redshift. In this case, we're talking about light that propagates parallel or anti-parallel to gravity. In the gravitational vertical direction, we're talking about light traveling vertical direction also. So now we're talking again in a spaceship in free fall. So in this case, special relativity apply. We're talking about a light that's emitted from the bottom here and received by a receiver at the top. Okay. And in this case, we do not expect any change in frequencies, so the received frequency is same as emitted frequency, and so there's no frequency shift. The subscript FF simply means free fall. In free fall frame, we see this result. Now we're talking about the same situation viewed by an observer outside. Okay, so in this case, you see the spaceship or the frame is falling in the gravitational field, and in this case, so the spaceship is falling. The during the light when emitted from the bottom to the top, and it was a height h, that the time it takes to go from the emitter to the receiver is h over c. And the receiver, but now, even during this short time, the receiver have gained velocity, because when you drop velocity by the acceleration times the time interval, so that's a change in velocity. So therefore, the receiver moving closer, so there's a Doppler effect. The wavelength is compressed, so it's a blue shift. So the change in frequency, fraction change of frequency is equal to the change in velocity, or rather the speed the receiver is moving divided by c. That's the Doppler formula. But on the other hand, we knew from the previous consideration, the receiver got the same frequency. It's no shift. So therefore, this Doppler shift, this Doppler shift must be canceled by some other effect. Okay. Now in this case, there is for this observer, he sees the space falling in the gravitational field. So therefore, there's a gravitational field, and suggests there's there's a gravitational frequency shift effect, which just cancels the Doppler effect. So the change in frequency is equal to because it just cancel. So here is plus delta u, here's minus delta u. So the sum will be 0. Okay. So therefore, the amount of gravitational shift is minus gh, the gravitational acceleration, times the height over c squared, or the difference in the gravitational field between emitter and receiver point, and divided by c squared. So this is the gravitational redshift effect implied by equivalence principle. So if I write out this delta to be between 2.1 and 2, so the omega 1 minus omega 2, the frequency divided by omega 2 is equal to minus the gravitational potential point 1 minus phi 2 over c squared. There's a minus sign here. So in other words, if the light is climbing to a high potential point, if phi 1 is less than phi 2, then this part is negative, so minus minus become positive, so omega 1 must be greater than omega 2. So the frequency of the received frequency is omega 2 is smaller than the emitted frequency, so this is redshift. Okay. Now if you shine light down, of course that will be a blue shift, but originally, Einstein thought some of this can be tested in astronomical situation, but turns out there's too many other unknown factors. It couldn't be done. And the first verification of gravitational redshift actually in an experiment on Earth in 1960. This is by Robert Pound and his graduate student Pound-Rebca at Harvard, and the height they use is just at the elevator shaft in the Harvard Physics Department, the Jefferson Lab, and the height is 22.5 meters. Okay, so therefore the gravitational field difference over c squared is going to be 10 to the minus 15. So it's a tiny, tiny, tiny frequency shift. Okay, but they were able to detect this. Uh, that's because a few years before that experiment, there's the discovery of the Mossberg effect. Normally, you can never define a frequency that accurately because the thermal recoil. Okay, and what Mossberg was for certain crystals, when the lattice is so stiff, the recoil is against the whole crystal, so infinite mass. So therefore, so the thermal recoil is negligible. So there, whatever uncertainty came from quantum mechanics, delta E delta T over h bar. So therefore, in order to have a sharp frequency, which is small delta E, you need a long lifetime. So Pound-Rebca to look for nuclear reactions. It turns out in some cobalt weakening decays and that goes into an excited state with iron. The iron went to the ground state by emitting a gamma ray. In that case, it's involves a high, uh, a long lifetime, so a very sharp peak. So therefore, if this emitted gamma ray from the bottom uh, through an emission like this, the same the iron sheet put on top can no longer be resonant absorbed. The reason because there's a gravitational redshift by this amount. So how can test? How did it know this amount? To verify this 10 to the minus 15 shift, Pound-Rebca did is they artificially introduced a Doppler blue shift by moving the absorber iron sheet towards the source. Okay, so because of gravitational is a redshift, by moving the absorber towards the source, so artificially introduce the Doppler shift to compensate. So therefore, how much this, so by knowing what kind of Doppler shift you introduce, you can find out how much gravitational redshift took place. So the question is, in order to cancel this, how much a Doppler speed do you need? Did they need? So therefore, this effect, well, because the gravitational, and so the Doppler shift must be just the velocity, Doppler speed over c, this Doppler formula, to generate this blue shift. So therefore, u must be gh to c cancel c, and the g is basically 10 meters per second square plus height 22.5 and divided by the speed of light and get something like 10 to the minus 7 meter per second. Now with this speed, you can easily show it'll take about 1 year time for the absorber to cover the height of the elevator ship. It's how small, how tiny a speed it is. But anyway, just the right speed, you find the gamma rays are resonant absorbed, and so verify the amount of gravitational redshift. This is really quite elegant experiment in 1960. Okay, the takeaway from this lecture, uh, so we have seen how the Galilean observation of the universality of free fall implies the inertial mass equal to gravitational mass, and then inspired Einstein to propose this equivalent principle that there's no gravity in a free fall, and in the mechanics that's just weak equivalent principle is same as this mass equality, but extend to all physics is called strong equivalent principle. For example, applied to electromagnetism, and it deduces effects like gravitational redshift, which verified by the Pound-Rebca experiments. Next lecture, number 8, we'll talk about, from this, we're going to talk gravitational time dilation, showing the clock at the higher potential points actually runs slower. And also we'll show that all these effects are needed to to make the GPS, the global position system, the GPS in your pocket work, you need to intake into special or general rotary corrections, all to do with time dilation. Okay, so that's all for today.